All right. Thin lens equation, or equations, I guess. We're going to use the equations that we have already learned with mirrors, and I'll just write them down. 1 over f, 1 over di, 1 over do. We've seen these before. And the other equation is the magnification equation, which has two forms. It can be hi over ho, a ratio of the heights of the image in the object, or it can also be a ratio of the distances, negative di over do, and it needs the little negative sign to adjust for some of the virtual things that happen with mirrors. So the real thing to remember is we have this issue where we have images that can be real or images that can be virtual. And with mirrors, we can have focuses that are real and focuses that are virtual. And so the same problem occurs with lenses, and we have to just be careful with our signs, pluses and minuses, to help the math understand so that you get the right answers. Now, it's called the thin lens equations because it's based on using similar triangles. I mean, when you draw a simple picture here, if we draw a mirror or a lens, I can draw a lens like this. We put the optical center down the middle. I can put an object here, give it a focus and a C, and we can draw, our little lines, and we get. Whoops, I'm doing mirrors. I should have done the lens. So hang on a second. We'll put a focus on this side too. Okay, so for refraction, right, if you come like this, we know that this is going to converge through the focus. We've already learned all the rules. And then you'll get, if you go through the focus like this, you will converge this way. And we get an image somewhere over here. So there's the picture. Well, when you look at all the things here, you can see that there are triangles that form. And so these equations are formed by using these triangles and what we call similar triangles to make relationships between the sides and angles. And that's where these equations come from. But the problem is we have to make a couple of little assumptions for these equations to work. And that is the lenses have to be very, very, very thin. Otherwise, we get small errors that creep into the equations. So even though we draw our lenses like this so we can see them, the reality is that what we're really talking about is something that is just barely thicker in the middle than it is on the ends. So it's more like a thin. The wider this goes out, the more error creeps into the equation, right? So even though we draw them like this so it's clearer for us to see what's going on, we have to remember that the lenses actually have to be very thin. When we draw our diverging lenses, the reality is these lenses are very, very, very thin like this because we have to keep them thin to not have too much error creep in. Now, if you have a thicker lens, you would have to make adjustments to these formulas. Right? When you get your degree in engineering or physics, optics down the road, you'll learn how to make the proper adjustments for thicker lenses and different effects. But for now, just learning the basics, this is where we're at. So the thin lens equations, right? And it applies to the mirrors too, right? We always draw our mirrors like with these big curves in them like this. But the fact is, it really only works for mirrors that have a very slight curve like this. Anyway, that's why it's called thin lens. Okay, so let's take an example. Let's just go through and look at some of the scenarios that might happen. Let's take a converging lens and let's draw one of the pictures and see what we can figure out. Because we want to sort of explore what happens in these pictures and what ends up being positive and negative and so on. Okay, so I'm going to remind you that for di and d, for di anyway, plus means, plus and minus have a meaning, right? In mirrors, we said that a minus would indicate a virtual image. But we also saw that the virtual images occurred on the opposite side of the mirror than the object. Remember that? They were in the mirror land. So there's a certain meaning for di. And there's also focus. The focus can be plus or minus. And again, it was because a virtual focus was negative for mirrors, remember? That also means, if it's virtual, that it occurs on the opposite side of the mirror. And so I think with lenses, it's a little easier to think about pluses and minuses by comparing what side things are on, as opposed to virtual and real, because lenses can give you real images on the opposite side, which is a little bit strange. Okay, so we're gonna discuss how that works by looking at some examples. Okay, so I'm going to draw myself a converging lens. We'll start with the converging lens because it's the one that has sort of the most options. I'll put a focus here. Here's my optical center. And I'll, of course, because we can come from both sides, we need a focus on both sides. I'm not even going to put the centers of curvatures in here because we don't really use them all that much for the lenses. So let me just put the focus. Here's one. Whoops. I don't know why it keeps jumping to the thick line. I have to figure out how to make that happen. There we go. Okay. Good. Let's take an object. And let's put them here. Let's put them in green. Doesn't really matter. Let's just put it, say, about here. So green is the object, and I'll put a little O beside it to remind us that that's the actual object. So that has to be real, right? That can't be virtual because that's the actual object. Now, having said that, it's possible for a virtual image in a mirror to be also in another mirror. You can do some pretty clever things by putting mirrors back to back and so on. But for today, we're just going to understand that objects are real, okay? It is possible to reflect a virtual image, but we won't get into that just yet. Okay. So let's draw some lines. Let's go, remembering our rules for refraction. Remember the whole difference between lenses and mirrors. Mirrors are reflection and lenses are refraction. So if I draw a parallel line, parallel to the principal axis across like this to my lens, I know it has to go through a focus. It has to refract. Well, it certainly can't bounce back to the focus on the right side because that would be reflecting. It has to bend. So it has to bend as it goes through this thing like this, through the lens. So there's rule number one. And then rule number two says, well, what happens if you pass through the focus and refract? Well, if I pass through the focal point, right, there's two F's on the picture. But if I go towards the focus on the other side, on the left side, well, I'm just going to sort of bend down, and I really don't know where that's going to go. It doesn't really give me any, because think about it, it certainly can't go parallel, right? The rule is it has to refract in a way that it's parallel. So watch what happens if I aim for the focus on the other side. I get to here. I have to bend, and I have to bend this way, right? That's how refraction works, because I've gone into this more dense medium. So I have to converge, which means I have to go down somewhere like this, but none of those lines can be parallel to the principal axis. So the rule won't work if I aim for the focus on the other side. But it will work if I aim for the focus on the same side. And here's what happens. If I aim for this focus and I go through here, I'll hit the lens. And now I'm on the bottom half of the lens, which means I'm going to bend up this way. And I can bend that way and become parallel to the principal axis. So you have to kind of keep in mind what you're dealing with. You can't just draw lines willy-nilly. And that puts my image, right here. So I've located the image using the rules. So there's what it looks like. Okay? Now, let's put some numbers on this picture. Let's say that, we start with an object, and we say that the object is, well, let's say it's 6 centimeters away from the lens. And let's say that the focal point of the lens, or the focus of the lens, the focal length, I should say, is 2 centimeters. Right? Well, let's see what happens with our equations, and let's see how we can get the numbers to match what we see in the picture. So let's start with the 1 over f equals 1 over di plus 1 over do. Now, let's talk about the focal length. you'll see here, I'm using the focus that's on the same side as the object, right? So if I use a positive number for the object, 6 centimeters, and the focus is on the same side, then it should have the same sign. So I should use a positive 2 for my focus. So let's try that and see if it works out. So I'm going to write over here that my focus will be a +2. And the reason is because it's on the same side as the object. Right? The F I'm using is on the same side as the object. So in math, pluses and minuses are telling the math where things are. Same sides should have same signs, and opposite sides should have opposite signs, okay? So let's use a 2 and see what happens. Let's just put that in there. Okay, and we're going to figure out what the DI is here, so we'll just leave that alone. And then the DO, we said, was 6. Okay. So you see the 2 and the 6 have the same sign because they're both on the same side of the picture. That's easy to remember. So let's work it out and let's see if the answer makes sense. And then we can use those assumptions. So what I'm going to do is just, I'll work over here so I can keep the screen where we can see it. So what we end up with is 1/2 minus 1/6, which equals 1 over di. Okay, and so 1/2 minus 1/6, if we can just do a common denominator here and change this to 3/6 minus 1/6 equals 1 over di. Okay, and then we get 3/6 minus 1/6, which is 2/6. And then we have to do, that's going to be 1/3, right? If we reduce that fraction to 1/3 and then flip both upside down, we get 3 centimeters for our DI. Okay, 3 centimeters. Now, here's the tricky part. We've got a +3, not a -3. Now, I look at the picture. Well, what did a plus DI mean? It meant that it was a real image, right? Now here we have a real image, but it's on the other side. So you see the problem. We can't use a minus for both because it kind of cancels out. So the DI comes out to a positive number. Okay. And it becomes, that means it's a real image. So even though we use the focus on the same side, but you'll also look in the picture, we also use the focus on the other side, right? We use both focuses. But the other thing to remember is that both of these focuses are real focuses. They're places that you can put your finger and touch. They're not inside some mirror land or lens land. They're not virtual focuses, right? The light actually focuses on both of those places. If you take a lens and you push the light through this way, it'll focus on this side. But if you push the light through this way, it'll focus on that side. But they're both real. They both are in the real world. So it makes sense that we got a positive answer here for the real DI. So now let's go on and figure out the magnification. If we figure out the magnification, that would be negative DI divided by DO. And we would get M equals negative 3 over 6, which comes out to negative 1/2, which means that the object is, or the image is going to be half the size of the object, so it should look a little smaller. And in our picture, it does look a little smaller. It's just a sketch, so it's not perfect. So that makes sense. And we also have a negative magnification, which indicates an upside down image. And that makes sense, because in the picture, we have an upside down image. So it seems like our numbers made sense, and they give us an answer. So we used a positive F because the focuses are in the real world. And we used a positive DO, obviously, because it's always real. And we got a positive DI indicating a real image. Okay, let's carry this through then, and let's keep using this. So what we're basically trying to do is use a positive for anything you can touch, and a negative for anything that's only sort of an illusion of where the light comes from. Okay? Okay. So in this case, we did not have to imagine any light rays, did we? So therefore, there was nothing that was virtual. Let's go on and do another example. Let's take the same converging lens and let's draw our here. Let's put a focus here and let's put another focus on the other side. These are real focuses. Focal points for a converging lens are real, so they should always be positive numbers. Now let's have a look at what happens if we take this object and we put it right in close like this. This time we're on the other side of the focus. See if that makes some kind of difference. Okay, actually I'm going to just move my focus a little bit so my picture can be made more clearly without having to fake. Oop, that's supposed to be black. And not thick. Oh, smart board. If only you were really smart instead of just being kind of smart. Okay, I'm going to put the focus sort of about here. There, just so the picture can be made without too much trouble. Okay, let's do our rules. Let's do our rules and see what happens. So we'll start with rule number 1. Well, let's go parallel right there. Again, I want the thin line parallel to the principal axis, which means this has to, no, it has to converge, right? So it certainly can't go through this focus on the right. There's just no way it can get through there. So I can't use that. I have to follow the rule and use the focus over here. So there's my rule. Okay, now, the next rule is a ray on a line through the focus refracts parallel. So again, let's try to imagine what might happen if I try to go on a line towards the focus over here on this side. If I aim for that, I'll hit the mirror like this. But again, it's a converging mirror, which means this line cannot bend up. That would be diverging, right? It has to bend sort of this way. And if I bend it that way, look, there's no way I can bend it that way because I'm aiming for the focus. I'll always fall short. So the rule won't work if I try to use this focus because it's a converging mirror and it has to converge. But the rule will work if I imagine lining up with the focus over here. Imagine lining up with it and going this way, right? So we don't actually draw all that. What we do is we just line it up and go like this, and we can see that the line is lined up with this focus over here on this side. And if it's lined up, when it refracts, it will bend and it will go like this. Okay, great. That works. The rule can work. But it leaves us with a problem. There's no crossing of the rays, which means there can be no image over here on the mirror, right? And so what happens is the only way I can get an image is if I imagine where these light rays came from. If I imagine that this light ray came from back here like this, right? And then I imagine that this other ray came from, oh, wow, came from back here like this. Let me just make that a little better. Okay, whatever, like that. We can see that they're going to cross, and I'm going to get sort of something here. But that's not a real image, is it? Because it's not formed by real crossing light rays. It's only formed by where we imagine the light rays to have come from. So an eyeball looking over here at these light rays, they wouldn't see the green object at all. Remember, this is the magnifying glass we talked about. What you would see is an image, which is the purple arrow, but it's a virtual image. So what will happen then if we start using our numbers? Well, let's say that we place the object, so DO, it can't be very far. Let's say it's 1 centimeter. And let's say that our focal length is 3 centimeters. So let me just put that over somewhere. The distance to the focus is 3 centimeters, like that. And let's see what happens. Clearly, the focus has to be larger than the DO, because look where the object is sitting, right? It has to be less than 3. So we're going to say that F is going to be 3 centimeters, but we have to decide about this negative thing, okay? And we're going to say that DO is 1 centimeter. All right. Let's put the numbers in. Well, if we just do it like this, if we do 1 over F, now, both of these focal points are real focal points. No matter which one I use, they're both in the real world. So that real light can actually bend through both of these focuses. It depends which side I go through. So that means that I should use a positive number, right? So let's see what happens. Let's see if we get the right instructions coming out of this. Well, what we get is 1 over 3 equals 1 over DI plus 1 over 1. And if I just move over here to finish that, then that would be 1/3, take away 1, right? 1 over 1 is 1, equals 1 over DI. Okay, well, if you have a third and you take away 1, that actually is negative 2/3, right? Because 1 is like 3/3. So 1 take away 3/3 is negative 2/3. That equals 1 over DI. But we still have to flip them, right? We have to flip them. So if we flip them, we get negative 3 over 2 equals DI. 3/2, so 1.5. Okay, so if we're looking at my picture here, I can see that I may have messed it up a little bit. Because my picture, if you look at my picture, you see this line up here, the red line. It's not very good. It's all kind of all over the place, right? And if I was a little more careful with that, let me go back and just kind of adjust that a little bit. See this? Let me get rid of that red line the way it is. This is the problem with sketches, right? If you do it too fast, a little tiny thing can make a big difference. So if you look at that red line, whoops, no, I don't want that. Let me get rid of that. If you look at that red line, the way I drew it, it was pretty messy. If I try to extend it back a little bit better, maybe like that, you can see how much difference it is. So that's where our object should our image should actually be. It should actually be a little bit maybe over there. Okay, but we're going to find out, because look what we've got. We've got 3/2. So 3/2 is 1.5. So that's what our DI is, 1.5. And mine looked funny, because if it's 1 to the green object, well, that's not 1.5. My first object is a little off. So see how I have to, you always got to be thinking about these things when you go through these. So that's more realistic. My picture's a little better, and now it matches the numbers, which makes sense. 1.5, a little further. Now, why is it negative? Well, it's negative because it's a virtual image. That's what negative means. And why do we know it's virtual? Because if you look at the lines that meet right here, whoops, if you look at those lines, they are not real light rays right here. We had to imagine those light rays going backwards. From the eyeball that sees the rays over here has to imagine where those rays came from in order to find the image, to see an image. So that means it's virtual. And that makes sense, a negative number. So it looks like we're okay. We're still using the same idea here of a positive F, and we're still getting the right situation. Now let's try the magnification and see what it looks like. Magnification is negative di over do. So in this case, it would be the negative of negative 1.5, right? Because my di is negative, and then my do was, I think, 1. So this comes out to 1.5 over 1, right? Did I put those numbers in the right spot? Let me just check. I think so. 1.5 over 1. Well, that's 1.5. Watch, you can do it like this. Well, basically, it's just 1.5. Anything over 1 is just 1.5. So we would have 1.5, and these two minuses would make it plus. So I have a positive magnification. 1.5 means that the image is 1.5 times the size of the object, which means it's bigger. It's 1.5 times. That makes sense, because look, it's bigger. I know mine looks more like twice as large, but that's because it's a sketch, right? So it's just to give us a hint. And then over here, it's positive, which means it's upright. And voila, it's upright. So far, our idea of using a positive number for f, because the focuses are both real, is working out great. And that will work pretty much for every converging mirror picture that you can think of. So we can sort of, converging lens. We can just remember that for our rule here that we found is that converging lens, f is positive. And it works every time. It works when you are outside the focus, like the first example, and it works when you are inside the focus. And that's because f is positive, because if you come this way, all the light rays will converge like this to this real focus. I don't need any dotted lines. But if you come the other way, the light rays will all converge on this focus, which means they both have a real focus in the real world. And so a positive number makes sense. Okay. Now, what is interesting is the DI. What you'll notice in the first example is the DI turned out positive because it was in the real world, and that's because it was formed by the crossing of two lines. So we're not really looking at opposite sides. We're looking at whether or not it's formed by real light rays that are crossing. But in the second example, it's important to see that it was formed by these dotted lines, which are imagined light rays. They are not real. So therefore, that makes sense, a virtual image. All right. Now all we have to do is look at the diverging lens and see how we could deal with that one. So let's have a look at that. So for a diverging lens, if we draw a picture of one, the diverging lens is a little bit trickier because the rules are tougher to make them work. Right? Now, we put this thing called the focus here, right? But here's the interesting thing. Let's just draw some light rays. If light rays come this way, they have to hit the lens, but they must diverge. They cannot go through this focus right here. They have to diverge outward. So the light rays have to do this. And so no matter where they go, they're not going to pass. One light ray might, the one that goes through here will pass through that focus, but all the other ones will not. This is what a diverging lens does, which means there really is no real place where you can focus. And if I do all of this backwards from the other side, if I take the light coming from this side, it's the same problem. It will diverge. Right? It's always going to be spreading out. So technically, there is no focus, or at least there's no focus for for real light rays to cross. But if I extend these lines backwards, let me use a different color so we can see where they might look like they came from. an eyeball watching these rays and saying, oh, look at all these rays that are hitting me. They look like they're coming from a place inside the mirror or inside the lens, sorry, that looks like this. So this is what we call a virtual focus. In the real world, you could never focus light with a diverging lens, but it appears to focus sort of inside the lens. What's important to realize is this is not in the real world. You can't go behind here on this side and see this image. It only works if you're looking into the lens and you see it inside the lens, right? You have to be looking this way, like the eyeball. You see this focal point inside the lens. But if you walk around to the back, it isn't there. There won't be focusing light rays there because none of these purple rays are real. They're virtual rays. So we have a virtual focus that only occurs. It looks like it's in the real world, but it's not. It's because of the light rays not actually being there. So that's very important. If you go back to this one, when it went to the other side, it was real light rays that crossed. See the difference? That's the difference. So we have a virtual focus, which means we should be using a negative sign for our focus. Let's do an image and let's see what happens. Okay? So let's draw a picture again. This time we'll draw a nice one. Ooh, I don't know if I want to do it in purple though. Let's go back. I tried to erase that. There we go. Let's do it in black. Like this. Let's make a nice diverging lens here with an optical center, sort of an optical center. We'll put some focal points on. Like that. Remember, these are not real focuses. Light never focuses in a diverging lens. It only appears to focus if you peer into the lens, look inside of it. Okay, let's put an object, and let's put the object, say, maybe here. And let's see what happens. So there's my object. So let's draw some rules. Let's do rule number 1. Okay, so parallel to the principal axis. There it goes. Now remember, it has to refract on a line through the focus. That's the rule. So let's try and imagine what would happen if I say, well, let's try to aim it for the focus on the left side. Well, that would be sort of down this way. That won't work because that light ray is converging, right? It's not diverging. This lens spreads light out this way. It has to bend up towards the top. So that is not going to work. So I can't even use that focus for this particular rule. But if I use the focus over here on the right side, and I imagine a line through the focus, I could diverge this line like this on that same line. And of course, we don't draw all those dotted lines because it's too much confusion. We just line it up with our ruler, and we see that it goes there. Oops, that's not very good. Let me sort of try and line that up a little better there. So you see, you have to remember what kind of lens you're dealing with. Now let's do rule number 2. Let's do a line through the focus, right? So if we've used this focus for rule number 1, you'll recall back in the very first example, we used the other focus for rule number 2, right? Well, do you think that would work here? Let's imagine what would happen, don't draw this yet, if I go this way. Well, I'm going to have to refract, sort of, I have to diverge out, right? I have to bend outwards. Well, if I bend outwards, how can I be parallel to the principal axis? It'll never work, right? So let's ignore that focus, and let's see what happens if we aim for the other focus. So if I aim for the other focus and I hit about here, now I can bend outwards and go, whoops, and then go parallel to the principal axis. See how it works? So that one does work. So I'm using the other focus again for rule number 2. It's almost like you have to use 2 different focal points for the 2 different rules. And again, I'm stuck with the situation where they do not cross because a diverging lens never crosses real light. That's what diverging means. The only thing that you can do is you can imagine what an eyeball might think or see. if it saw these diverging rays, it would see them as if they came from somewhere back in a straight line, right? That's how we perceive the light. And here is where they cross, and there's my little image. Okay, let's put in some numbers and see if we get the right answer. That makes sense. So let's add some numbers to this picture. Let's make the focal point right here. I don't want to use purple. Let's use black. I thought I pressed black. Let's make the focal point right here. Let's call that 3 centimeters. Now my object, of course, is further away. That looks more like, I don't know, maybe 4 or 5 centimeters. So let's call it 5 centimeters. Because it's bigger, it's a further distance, right? So to match the picture, that makes sense. Okay, now let's do our mirror equation. 1 over f equals 1 over di plus 1 over do. We said that our focal point here in a diverging lens isn't real. It never focuses light. You can only get a focus virtually by extending the light rays backwards to see where they appear to come from. So we're going to use a negative number. So that little number up there that I picked, that number 3 for the focus, is going to be a negative 3 for this lens. So let's put 1 over negative 3 and see what happens to our di. Of course, our do is always a positive number, and I think, what was it? Let's go back, 5, right? Let's check. Yes, the object was 5. Because it's always in the real world, so to speak. Let's do the numbers and see if they match the picture. Okay, so we have negative 1/3 minus 1/5 equals 1 over di. So if we do some common denominator here, or you know, you can convert them to decimals, however you want to do the subtraction, that would be 5/15, multiply the top and the bottom by 5, and then multiply the top and the bottom of this other fraction by 3/15 equals 1 over di. So we have negative 5 minus 3, which is negative 8, right? So we get negative 8/15 as 1 over di. And so that means that if we go negative 15 over 8, we get our di. So 15 over 8 is just a little bit less than 2, isn't it? If that was a 16, it would be right on 2, right? So you can just grab your calculator if you want to know the precise number and do 15 divided by 8. That's about 120. Whoops, no, my calculator is messed up. 1.875. So we'll call it 1.88 di. Well, let's go see if that makes sense from the picture. Well, kind of, doesn't it? Look how close it is here. That could be 1.88 with our other numbers. That sort of makes sense, right? It's less than 3. It's inside the focus, so that's good. It's a negative number, which means it's a virtual image, which means it must be formed by imagined light rays, right? Or apparent light rays. And it is. Dotted lines mean virtual, so that negative makes sense. And then if we do the magnification, we'll do magnification equals negative di over do, and we get this. We get negative 1.88 over 5, right? I think I'm going to just check. I think do was 5. Yeah. Okay. And so that becomes a positive number. That works out to positive 1.88 divided by 5. So we can do that on our calculator. I'm actually going to use 1.875 just to get more accurate. But if you do, well, maybe I won't. Then it'll confuse you. Okay, 0.376 is what that comes out to, and it's a positive number. So that means that's just over a third. A third is 0.33. That's just a little bit over a third, right? So this means, because it's a decimal, it means that the image is smaller. It's only 1/3 the size, or a little bit more than 1/3 the size of the object. Well, look at my picture. It's very small. It makes sense. It also comes out to a positive number, which means it should be upright. And of course it is. So what we've learned here is that we can understand some simple rules for assigning the negative signs to the lenses. Okay? So in a converging lens, we always have real focuses. And so the focuses are always positive. And we tried that in all the two different scenarios, and it worked. In a diverging lens, we have virtual focuses. There's no way a diverging lens can actually focus real light. You can only find a focus by extending the light sort of backwards. And therefore, focuses should be negative for all diverging lenses. Now, what's interesting is the DI part. The DI kind of worked itself out in every one of our examples, right? For the diverging lens, the DI is always going to be negative because there's no way to get a real image in a diverging lens because it never converges real light. So it's always going to be a virtual image. So that means that in a diverging lens, if we talk, so those are for the Fs, the rule for the DIs, in a diverging lens, DI is also always going to be a negative number. It's also going to be a virtual image every time. So there's no way to get a real image. So if you were doing a question where you had to start with the DI and solve for the F or solve for the DO, you'd have to remember for a diverging lens to use a negative on DI because it's always a virtual image. But DI is a little bit tricky for converging lenses. I'm going to go right back to our first example. We did this first one, and we got a positive DI, a real image. So that was a positive DI. But notice where we are. Notice the object is out past the focus. We get a positive DI. But when you move in past the focus in our second example, look what happened. We got a negative DI. See, our object is now inside the focus. We got a negative or virtual image. So for the converging lens, it's a little bit trickier. For the converging lens, actually I don't need that line there. For the converging lens, the DIs are a little bit tricky. You get positive DI or a real image if the object is beyond the focus or outside the focus. But you get a negative DI or a virtual image if the object is inside the focus. Now, if you're solving a question for DI, it works itself out. You don't have to worry. But if you're using a number for DI and you're trying to figure out the F, you would have to remember this little rule. And if your object was inside the focus, you would have to use a negative number for DI. But if your object is outside the focus, you would have to use a positive number for DI. And remember about real and virtual images. Does that make sense? Okay. So for instance, we could do an example of a question where you would have to think about the DI in a converging lens. So let's do this. An object is placed 2 centimeters from a converging lens. The image appears to be 0.8 centimeters from the lens. What is the focal length? Okay, so what they're telling you here in the picture is if you draw your picture, there's my lens, you put a focal length. We don't know what the focal length is, but we'll just put the focuses in there and call them F. But look where the object is. The object is 2 centimeters from the lens. Wait a minute, I think I did that backwards. Yeah, that's not what I want. I'm sorry. I'm going to have to change this number. Let's say that this number is going to be a better number to make sense. Object is 2. Let's make it 2.5, a little bit further. Okay? All right. So if you look at this, question, how do we know if the DI is a negative or positive? If we want to solve for the F, if we want to find the focal length, right? Well, it's going to be tricky. We're going to have to sort of take a couple of guesses and try to figure it out from what's going on. It might be simpler for me to illustrate this if we say we have DO, DI. Instead of solving for F, if we solve for DO. But let's just see what happens. Let's just carry on. So let's try it. If the object is outside of F, then, right, let's say we put the object outside of F. And we do our rules. Through the focus. Through the focus. Right? We get an image over here that's upside down. So if this was 2, could this be 2.5? Hard to say. Almost looks symmetrical. Well, let's look at the other possibility. What if the object is inside the F's? Let's put the object here. Whoops, a little bit closer. Let's put the object, oh, rats. Let's put the object a little bit closer. F, maybe right about here. Well, remember, we have to do the funny rules here. We have to go through, this is through the focus and parallel. And then this is parallel and then converging through the focus. And this is where we get this thing happening. We get this bigger image over here. That kind of looks more like what we're talking about, doesn't it? Because this would be 2 from here to here, and this would be 2.5, where the image is. So it seems like from this information, it seems like the second picture is a better fit. So we should be thinking that the object is inside of F instead of outside of F, which means when we use our DI, we would have to use a negative number. Okay? So you see how you can't just memorize negative, positive. You have to think about the scenario and try best to match whatever the numbers are in the question with a sketch or a picture to give you an idea of whether you should be using a plus or a minus. So if we do the minus, then we have 1 over DI equals, we have 1 over F. Let's start again. 1 over F equals 1 over DI plus 1 over DO. And we know that this is a converging lens, so we know the F is going to become positive. So we hope that it works out to a positive number, or else we've got a problem, right? So let's see what happens. We're going to use our DI of 2.5, but we're going to say that it's negative because we think that this is the scenario and we think it's a virtual image. So we'll use negative 2.5. And then we have plus 1 over 2. Well, let's see what happens. We get 1 over F. Okay, let's just use decimals this time. Let's take 1 over 2.5, which is the same as 1 divided by 2.5. So that's a negative 0.4, but then this is a plus 0.5, which means that 1 over F is equal to a positive 0.1, right? And then if we flip it to get the f, and we do 0.1, and we do a 1 over, we get 10, a positive 10 as the focal length. That makes sense. A positive focal length is necessary for a converging lens. So it's a very strongly focusing converging lens with 10 as the focal length. So the focuses are easy. The focuses will always be real or virtual. And so we can make a rule for converging lenses, f is positive. For diverging lenses, f is negative. For the DIs, it's a little trickier because the converging lens has a couple of options. So you might need to think about a sketch to give yourself an idea of what best suits your numbers before you go running through the equations. Other than that, though, that's all there is to it. So we'll stop there.